All right, so part 2. We're talking now about simple harmonic motion. These are the ones that you're going to have to set up and create your own trig functions. We stick to sine and cosine functions, and we tend to keep them pretty simple without phase shifts. Simple harmonic motion, there's lots of different models. Here we've got a sketch of the spring as our simple harmonic motion. You can also see pendulum models where you're going back and forth and back and forth. And another common one is also waves, like high tide and low tide. Really, it's anything where the movement is repetitious. We call it simple because we're going to ignore some pretty important things like friction and air resistance. So, for example, if I imagine that I have the spring hanging here, we would call the hanging point where it's just at rest, we would call that equilibrium. So notice that they have marked the center of the ball, the center of the weight on the spring as 0. This is like your midline on your sine or your cosine function. And then what they're trying to indicate here is that at its lowest point, it goes all the way down to 10 centimeters. And at its highest point, it's going to bounce all the way back up to a positive 10 centimeters. So notice it's negative, and then it's positive when it's at its highest point. So it's equilibrium, that's our center line. And then you can think of the height here as being sort of like the amplitude, the height here as being an amplitude. And so the total height would be 2 times the amplitude. It's called simple because in reality, if I pulled this ball down and set this into motion, right, friction, air resistance would cause this to not continuously go up to 10 and down to 10 and up to 10 and down to 10. It might go down to 10 at first and then maybe only bounce back to 9 and so on until it came to rest again at equilibrium. In simple harmonic motion, we assume that the cycle is just continuous, that it never stops, and it always goes to the lowest and the highest point. So it's a little bit oversimplified. It looks like there's one more note here. The time to complete one cycle, no surprise here, is called the period. So that would be the time it takes to go from equilibrium to the high, to the low, and back to equilibrium again. This can change. It could be that you start at the high, go to low, and go to high again. But regardless, it's the period refers to the time for one complete cycle. So let's flip this over and see the model for simple harmonic motion. There are 2 that we'll stick with, and we can write them as D standing for your distance from the origin or from that center equilibrium line. So D is equal to A, your amplitude, times the sine, and then here instead of using B, they tend to use omega, so omega times T. Omega is what's controlling your period. Your amplitude is your A. Your period, because it's a sine function, is 2 pi over omega, and we have something called the frequency. Think of this as like how many periods you can fit into 1 unit of time. So it might be how many periods in a second, how many periods in an hour, it would depend on your unit of time. We can also add in, with all the same notations about what A is and what omega is, D equals A times the cosine of omega t. They both operate the same way. The difference would be to look at where your starting point is. How do you choose which one you want to use? Because you guys will be creating your own models. So which one? It has to do with where you're at when t is 0. Because your sine function, when t is 0, starts at 0. That would mean that if you choose the sine function, you're saying that at equilibrium, at time 0, I'm at equilibrium. If you were at the cosine function, right, then that would imply that time 0 is going to have you either at a high if your A is positive or at a low point if your A is negative. So you can use sine and cosine sort of strategically to correspond to with your location at t equals 0. So let's try one. In example 3, it asks me to go ahead and create an equation for the harmonic motion of the ball on the front side of the figure. And they've given you a little bit of information about the period. We'll stop there with that question first, and then we'll work on the frequency question. So if we look back on the front side, it did say that the ball was going to start at equilibrium. So at time 0, I want to be at that 0 line. And so I'm going to select D equals A times the sine of omega t as my equation. If you look at that front picture, here I've got another copy that I can throw on top here. Right? It said that we were starting at equilibrium, and if we look at our picture, we are going up 10 units and we are going down 10 units. That makes my amplitude equal to 10. And your period can be calculated as 2 pi over omega. I actually know the period, it's 4 seconds. I need to calculate what omega should be in order to set up my equation. So in this case, a little cross multiplying, 2 pi is 4 times omega. If I divide out the 4, then my omega is pi over 2. And so I can write this equation as 10 times the sine of pi over 2 times t. Quick reminder, why did I select the sine function instead of the cosine? Because the ball at time equals 0 started at that center line at equilibrium. The frequency, right? So this is the answer to the piece about the equation or the model. The frequency is how many cycles you can fit per unit of time. And there's actually an equation for that. It's right up top here. And it is the frequency is omega over 2 pi. So given that we have now calculated pi over 2 as our omega, we can just divide by 2 pi. And instead of dividing by 2 pi, we'll multiply by the reciprocal. My pi's will cancel. That means I'll take a quarter of a cycle for every second. My period was measured in seconds, and it took me 4 seconds to go 1, so it's a quarter per second. That makes sense. I'm going to press stop here before we get to the last one, and there'll be one more part for you guys.